Hello everyone. The topic of my presentation is development and volumetric change evaluation of geopolymer binders in water curing regime. So we'll quickly go over the outline, which is the introduction, the experimental work involved, the results and discussions on the tests that we conducted, and finally the conclusions. The objective was to develop cement-free binders for the production of engineered cementitious composites. As we know that in engineered cementitious composites, we utilize a high content of cement for the uniform dispersion of fibers. So the aim was to develop cement-free binders using the industrial waste products like fly ash, slag, so that we can overcome the shortage of landfill sites, and also we can reduce the carbon emissions associated with the production of cement. Using the geopolymer technology or geopolymerization, geopolymer binders are developed through alkali activation of aluminosilicate-rich materials, which are also called the source materials or the precursors to the geopolymers. And using the alkaline reagents, which can be in powder form or solution form, the reactions that are involved in during the geopolymerization, the silica and the alumina from the aluminosilicate rich source materials gets into the solution with the help of alkalinity present in the reagents, and the tetrahedral compounds then combine with the help of oxygen atoms to form polymeric chains and hence polymerize. The problems associated with the conventional technique of geopolymer development. So geopolymer development has two techniques, the two-part production technique and the one-part production technique. The problems associated with the conventional two-part geopolymer production technique, that it utilizes solution-based reagents which are highly corrosive, and for achieving satisfactory mechanical properties, we require heat curing of the specimens. On the other hand, in the one-part production technique, we have powder-based reagents which are used in lower quantities than the solution-based reagents, and also we can prepare it as one part. By one part, we mean using the source materials and the reagents in powder form as one part blended together. We simply add water to it, like in case of cement-based binders, we add water to the cement. In the similar way, we add water to the pre-blended mix of source materials and the reagents. Whereas in case of two-part production technique, we prepare solution-based reagents separately, we prepare source material separately, and then combine them together to form a wet mix. So the literature available on shrinkage expansion indicates that we use a higher content of paste. The content in geopolymer, the paste content in the geopolymer concrete is relatively higher as compared to the OPC based concrete. That's why we have higher chances of shrinkage in geopolymer based concrete. The shrinkage mechanism, which involves water loss from the capillary pores due to the hydrostatic tension leading to the collapse of these capillary walls. Higher strength concrete with lower water binder ratios obtain lower values of shrinkage strength. That's why we used high calcium materials like fly ash class C and slag in our research in order to obtain higher strengths. And we also used calcium hydroxide and sodium metasilicates in order to maintain high calcium in the system in order to obtain higher strengths to mitigate the shrinkage effects in geopolymers. The shrinkage strains were higher in fly ash slag concrete than OPC concrete during the initial drying periods, and obtain almost similar shrinkage strains at 28 days. So the experimental program, the mixed proportions for one part geopolymers, we have two geopolymer binders. We have one cementitious binder. So the cementitious binder, the control mix, which is the paste component, of engineered cementitious, standard engineered cementitious composite. So that's why we try to maintain the content of slag or ground granulated blast furnace slag similar to the cement content in the control binder, and the fly ash content was also kept similar to the fly ash content in the control binder in order to achieve similar mechanical and workability properties as that of the control binder. So the experimental work consisted of compressive strength. The validation of compressive strength results with the help of microscopic analysis using scanning electron microscope, and finally the shrinkage expansion and mass change. So we can see that the mix CSN had a steeper curve during 7 to 14 days, because this mix has a higher slag content, and slag has a higher reactivity in comparison to fly ash class C. That's why it had a steeper slope during the 7 to 14 days period. And for mix CS, the curve was steeper during 28 to 56 days because of the combined effect of geopolymerization and the pozzolanic activity of fly ash class C, which resulted in higher strength gain for the mix CS during 28 to 56 days. The steepest slope was seen for the cementitious binder from 28 to 56 days because of the synergy between fly ash class F and cement particles, which led to 25.3% strength gain from 28 to 56 days for the control binder. So as we can see that the mix CS on the left hand side and the control mix FPC on the right hand side, the mix CS has lesser number of unhydrated or partially hydrated fly ash or slag particles in comparison to many number of fly ash class F particles in the control binder, unhydrated or partially hydrated fly ash class F particles in the control binder. So this indicates the mix CS is more denser than the control binder, which is responsible for the higher strengths for the CS mix at all ages in comparison to the control binder. So the length change with time. The control binder FPC exhibited expansion at all ages 0 to 90 days, whereas the geopolymer binders CS and CSN exhibited shrinkage at all ages. The mix CSN in red color exhibited relatively lower shrinkage strains than the mix CS because it had a higher slag content, which means higher calcium in the system, which facilitates the dissolution of silica and alumina ions from the source materials, which leads to more reaction products and more densification of the mix, and leading to lower shrinkage strains in comparison to the mix CS, which is in black color. So higher shrinkage strains were seen during the first 7 days because of rapid geopolymerization during the first 7 days, and the shrinkage strains reduced after 28 days, indicating the completion of the geopolymer reactions. Similarly, for the mass change as well, we have a steeper slope during the initial 7 days, indicating rapid cementitious reaction, rapid geopolymerization reaction, during the first 7 days. And in a similar way, the slope became almost constant after 28 days, indicating the completion of the cementitious and the geopolymer reactions, and which indicates also the refinement of the pore structures with the continuous development of reaction products. The shrinkage expansion of binders reduced with the increase in compressive strength with age, which is a result of the continuous development of reaction products, leading to the densification of the microstructure with age. So finally, the conclusions: the higher GGBFS content in the CSN mix resulted in up to 8.5% 30% lower shrinkage strains at 28 and 56 days compared to its counterpart mix CS. The shrinkage, expansion, strains, and mass change reduced with the increase in compressive strength of binders with age. The slope of mass change versus time plots was steeper during the first 7 days, indicating the rapid geopolymerization or the cementitious reaction. The rate of mass and length change declined after 28 days in the water curing regime for all binders, indicating the completion of geopolymerization or cementitious reactions. The binder CSN with an equal proportion of fly ash and GGBFS obtained 12.5% to 26.7% lower compressive strength at all ages than the binder CS, having 45% slag and 55% fly ash C. There seems to be an optimum threshold for the content of slag calcium in the system for the strength development. We are highly thankful to the funding agencies and our industrial partners.